Today we are going to start with a new unit, which is oscillation. So before going to this oscillation, you must know what is meant by a periodic motion. A motion which repeats itself after a particular time interval, it is called as a periodic motion. Now suppose this is a sun and earth is revolving around it in an elliptical orbit, which we have seen in an earlier lecture. This earth has a period of the 365 days, means every after 365 days earth is going to be back in the same position. Okay, so such a type of a motion is called as a periodic motion. Now if you take a spring and if you attach some mass to it, okay, which is suspended from the rigid support, and if I apply some force on this, okay, so this spring will keep on oscillating like this. So this is also a periodic motion. So any motion which repeats itself after a particular time interval, it is called as a periodic motion. If you consider a clock, in a clock we are having minute hand, hour hand and a second hand. Okay, so minute hand is having a periodic motion of 60 minutes. It means that every after 60 minutes, so this minute hand will come into the same position where it has started. Okay, so the hour hand, every after the 12 hours it will come into the same position after 12 hours. And similarly the second hand will come every after the 60 seconds to the mean position where it has started. So such a type of motions are called as a periodic motion. So in a day-to-day life we come across with a enormous numbers of these periodic motions. Okay, and we now let us see what is mean by oscillatory motion. Okay, so if a particle is moving in a straight line back and forth, okay, suppose this is a straight line, and if a particle is moving uh, forth and back about its mean position, okay, so such a type of motion is called as a oscillatory motion. Okay, for example, so the circular motion of this earth, or the circular motion of the earth, it is a periodic motion, but it is not an oscillatory motion. Okay, but this the mass attached to the spring, which is moving up and down, so this is a motion of an object along the straight line, so this is called as a oscillatory motion. Okay, so we can say that the every periodic motion is not a oscillatory motion, but every oscillatory motion is a periodic. So the motion of the particle along a straight line back and forth, it is called as a oscillatory motion. So the simple harmonic motion is the simplest form of the oscillatory motion, in which the particle moves in a straight line, okay, and in which this force, it is directly proportional to the displacement, and it is always directed towards the mean position. So if a particle is performing so forth and back movement from its mean position, and in which this force which is applied on this particle, okay, so if that force is directly proportional to the displacement, and if that force is always directed to the towards the mean position, then such a type of a motion is called as a simple harmonic motion. For example, suppose there is a spring which is attached from a rigid support, and which is so some mass m is suspended from the spring, and if I apply some force on this, and if I pull this spring downward, so the position of the spring, say let the displacement from the mean position be x, so this is the displacement from mean position, and now when I apply some force on this spring, the spring will start oscillate. Okay, it will move upward from this mean position also, and after some time, so it may reach over here also. Okay, so this displacement is also x. Okay, so the restoring force. Okay, now let k be the force constant. So this force constant is dependent on the elastic properties of a material. Properties of the material of the spring. Okay, so as this elastic properties are more, the force constant will be more. Okay, more the elastic material, more will be the force constant. Okay, let m be the mass of the object, or mass attached to the spring, and let x be the displacement from the mean position. Now according to the simple harmonic motion, we can say that this force is directly proportional to the displacement, okay, and it is always directed towards the mean position. Okay, so the displacement and force are in opposite direction because this force is always directed towards the mean position. So this force is a restoring force. So this restoring force is directly proportional to the displacement and it is always directed towards the mean position. Therefore, we have taken this minus sign. So this F is equal to minus K into X. Now, according to the Newton's second law, we know that this F is equal to a mass into acceleration. So I can write that A is equal to F upon M, or I can also say that, so this F is equal to minus K into X upon M, as this force is a restoring force and as we are dealing with a simple harmonic motion, so we have put the value of F as minus Kx. Now let us define a new entity which is called as the angular velocity, omega, and omega is equal to square root of K by M. Now this angular velocity omega is directly proportional to the force constant if we are considering any type of a motion. Okay, so this force constant is more will be the angular velocity, because we know that this force constant is directly proportional to, or it is dependent on the elastic properties. More will be the elastic properties, more will be the force constant, and more will be the angular velocity. But it is inversely proportional to the mass, because see here, if this object, or if this object is having more mass, okay, if mass is more, its velocity or the angular velocity will be smaller, okay, because if the object is heavier, okay, it will take more time to reach at a particular displacement. Okay, so this omega is inversely proportional to the mass, but it is directly proportional to the force constant. Okay, so therefore we have defined a new entity which is called as the angular velocity omega, and which is directly proportional to the force constant, and it is inversely proportional to the mass. Okay, or I can also write omega square is equal to K upon M. Now if I put the value of this K by M as a omega square here, so I can write, so this A is equal to minus omega square X. Now see here, F is equal to minus K into X, and this A is also equal to minus omega square X. So whenever we are dealing with a simple harmonic motion, the force is directly proportional to the displacement, and this restoring force is always directed towards the mean position. Acceleration is also directly dependent on the displacement of a particle. So in a simple harmonic motion, so the force and the acceleration are directly proportional to the displacement, and they are always directed towards the mean position. So this is what called as a simple harmonic motion.